This is part 3 of a series on geometrically interpreting the chain rule in multivariable calculus. My name is Bill Kinney. I hope you've watched the first 2 parts, though if you have, you might be wondering where the geometric interpretation is coming in, and that's where we want to focus this video on. Again, here's the formulas that we are using for the general chain rule here when a quantity z depends first on x and y, and then x and y individually both depend on u and v. In this example down here, u and v are replaced by r and theta, and we can write down this formula here as well as this formula right there. And then we can use the particulars of this example, in particular the fact that this capital phi function is representing a polar coordinate transformation, to simplify this even further for this particular situation. We can, for example, figure out the partial of x with respect to r, which is cosine of theta, and plug that in there, etc. And ultimately, look at these derivatives here as dot products, and looking at them as dot products is going to be the key to our geometric interpretation. But let me finish something off on this from the last video here. First of all, we were computing these partial derivatives for this particular example with more detail. Let me make this bigger, like the previous one is, and also color it red so we've got some consistency here. And let me also add in that this second one here could be found with the dot product. So look and compare in this particular situation where the capital phi function is a polar change of coordinates transformation. The partial of z with respect to r can be thought of as this dot product, and if you use the formula for f that's up here, that can be simplified to this first of all, which is the same as this, and then if you replace the x and y with their dependence on r and theta coming from these equations that are right here, then you can write that derivative in this way. And in the same kind of way, the partial derivative of z with respect to theta can be found and ultimately simplified to this. All right, so if you haven't done it yet, you should probably pause the video and double check these calculations on your own. I will now emphasize that another way to check all this, I emphasized this in the last video, is to focus on the function we are differentiating with respect to r and theta, that it can be represented like this, and if you differentiate that with respect to r, you should get this thing, and if you differentiate this with respect to theta, you should get this thing. So that's a check that it works. By the way, I also I used a double angle formula to represent this function in this way, and so you could differentiate this instead, and your derivatives would look different than what's up here, but it would be equivalent by, again, some double angle formulas. All right, let's focus now on how to interpret this geometrically. So what I have here is some Mathematica code that will generate a picture, a couple pictures actually, side by side, that we want to think about here to help us understand how to geometrically interpret the chain rule. Notice first of all how these plots are labeled. All right, you've got 2 planes here. You've got a plane on the left and a plane on the right. This plane on the left, the axes are labeled with r and theta. The plane on the right, the axes are labeled with x and y. I am thinking of this plane as being a copy of R2, the plane, 2-dimensional space, labeled with r and theta, the r theta plane, if you will, and this plane also being R2, but I'm labeling the axes differently, x and y. I might call this the xy plane. What this picture, first of all, is showing is that this rectangle over here on the left is getting mapped to this half annulus, if you will, half of a washer, if you prefer, than annulus, this half ring shape. The transformation capital phi, this formula right here, is what is doing that geometric transformation of the rectangle into the half annulus. We can take points r comma theta over in this plane on the left, plug them into that function, and get a corresponding point over here. For example, this big black dot here on the left is at the point at coordinates r equals 0.5, theta equals 0. that corresponds, that gets mapped to this point over here, whose x-coordinate is 0.5 and whose y-coordinate is 0, the same as r and theta back over here, but that's because its polar coordinates are 0.5 and 0 when you are on the x-axis. Those are match up. But if I move to some different point, and I can move this to a different point, for example, I can make r go up to 1, say, and let's make theta go up to about pi over 2. Pi over 2 is about 1.57. So maybe you overshot a little bit, right around there somewhere. So that point in this left-hand plane here has coordinates, rectangular coordinates, r comma theta equaling, let's say, 1 comma pi over 2. That, under capital Phi, gets mapped to this point here in the xy plane, whose rectangular coordinates are 0 comma 1, but whose polar coordinates are 1, the distance to the origin, comma pi over 2, this angle that the ray through the origin in this point makes with the positive x-axis. So this mapping is really doing the polar coordinate conversion. Here I'm still essentially on the y-axis over on the right with an angle of pi over 2, but r has become 1.5. If I go to an angle of pi and say I have a distance of 2 units away from the origin, and I'm up at the upper right corner up there, and it gets mapped to the lower left corner down here. That point has got coordinates, polar coordinates 2 comma pi almost. All right, I realize I'm already getting low on time here if I want to try to make this 10 minutes, but that's the, I'm realizing I'm going to have to do yet another video. That's the basic thing you want to understand first of all. Second thing you want to understand is you see a contour map in the background in both plots. This contour map right here is the contour map, the map of the level curves of the original function thought of in terms of x and y. If you were going to make a contour plot, the level curves of that function there, x squared minus y squared, the level curves would all be hyperbolas. If you set this equal to a constant, you get a hyperbola actually as long as the constant is not 0. If the constant is 0, then you actually get this x shape that goes to the origin, but otherwise you get a hyperbola. If the constant is positive, you get hyperbolas over here. These correspond to positive values of the function. You can see the numbers that they get matched to, 6, 8, etc. If you have negative values of the constant, like -2 or -4, you get these hyperbolas up here. So this is a contour map of the original function. What's this contour map behind here a map of? Well, it's really a contour map of this function in terms of r and theta right there. Now it's the same function when you think of it as a function of a point in the xy plane. You would use this formula if you use rectangular coordinates for the point. You would use this formula if you use polar coordinates for the point, and you'll get the same output. You can try that with different points, whether they be given in rectangular coordinates or polar coordinates. These two expressions will give you the same output, but they are different formulas, and so this is a little bit of an abuse of notation as well. This thing as a function of r and theta is not really the same as this thing as a function of x and y. They are different things. This is trigonometric over there, and this is not. They do result in the same outputs when you plug in points in the plane on the right, plug them into the appropriate formula based on whether you are thinking of those points in rectangular coordinates or polar coordinates. But as formulas, they are different formulas, in fact. But this graph on the left, this graph of the level curves here, is in fact the contour map of this function if you ignored the fact that x and y were ever in there. If you only thought about a plane on the left and you labeled it r theta, and you made a contour map of this particular function here, again, ignoring x and y, ignoring transferring r theta to xy, just thinking about this expression as a function of r and theta, you would get this plot right here on the left. That's in the background. I'm noticing that it's about 10 minutes here, so I'm going to stop this video here, but we'll go on and continue thinking about this in a fourth video.